Hello friends, सबको नमस्ते. So today in this video we will make a blood cell object detection model using a SSD model. So this is going to be a data set which contains label and images and label. In images, this is a, you can say, blood cells, and these are the labels of each images. Let me show you inside it. So this is your blood cell. Basically it contains the details of this one. First thing is a class index, and other things is the uh, other thing is annotation or bounding box details. And this values box values is in a normalized form, so we have to unnormalize them to use them in a model. Okay, let me show you the test images labels, but we do not need any labels here. We just need the images for the prediction part. So let me open this in a Jupyter. I already opened it. See this. So let's get started. The data set which we use is SSD 300, which is 16 bits, and here you can see that we have 91 classes: 88, 89, 90, and 91, and zero index value is already fixed for background, so we have to make the class index +1 to make sure that zero index is fixed for the background only. Let me show you one thing more, that how many classes we have. I think there is no YML file, so that I will show you what how many classes we have. So let me show you. See, the classes which we have platelets, RBC, and WBC. Okay, and zero index value is for the background 1, 2, and 3. So let's get started. So let me first show you how you can connect your zip file which is uploaded in your Google Drive to your Jupyter file. Let me show you first. Go to your Google Drive, copy the link, make sure that this thing is on anyone with the link. Okay, copy the link and just paste it here, and capped this part only till this slash, and remove everything from here to here. We do not need anything else, just need this. You can say this is your unique ID for your zip file, which is required to connect your Jupyter file with your dataset which is present in your Google Drive. Okay, let me run this cell. Now let me run this. This will download the zip file from the Google Drive. Say this. Now we have to unzip it. Say this is a dataset with 2 folders, test and train. Now these are the packages or libraries which we use for creating a CNN model with the blood cells dataset. The classification head which we use is SSD classification head. I will tell you the use of these utils in below the code. The weights which we are using is SSD 300, which is 16 weights. Okay. So let's get started. Before that, let me show you one thing. See this. When we train the model without pre-processing the annotation file, sometimes there is a error during training that particular annotation file is there but image is not there. And sometimes second problem with the annotation files is that sometimes annotation file is there but inside that annotation file data is not present. So how to solve this? And to solve this problem, we have to remove those annotation files. So how I am doing this? Let me show you here. And one more problem is there with the annotation file. Let me show you this. Sometimes this annotations files, this you can say the bounding box details. When we find a area of this bounding box, it will give us the zero value. It means bounding ultimately when we calculate the area of the bounding box, it shows us zero value. So this type of bounding box throw the error during training with some error message. So so this type of annotation file have to avoid this, or we can say that we have to kept those annotation details only whose area is greater than 0. Okay, means sometimes there is more than 5 bounding boxes details present in one annotation file. In these on these 5 bounding box details, one bounding box area is you can say is equal to 0. So we have to remove that bounding box details only and kept other 4 box value. We not completely we have to does not able to completely delete or we can say remove those particular annotation file. So how we have to do it, let me show you. First, this is the directories of annotation directories and image directory. Just give me the length, how many annotation files, or we can say number of images present before pre-processing. Okay, and here see while list right first it list all the annotation file name in this annotation directory. Now image set it will list all the image file name in the images variable. Now I have to iterate over the annotation. Now first I have to fetch the annotation file path and just replace the last .txt with the .jpg. Okay, this way I am doing it. -4 basically it will remove last four character from the string. Okay, this way I get the image file name and replace and add concat with jpg. Now is suppose first problem that particular annotation file is there but the image is not there in the images folder. So how we have to deal with that type of problems? Directly just fetch the image file name and just just search that image file name in this images variable. If it is present, it's okay. Otherwise it is not present, just remove that annotation file and continue. We do not want any further process with that annotation file. Okay, now second thing, new lines. What is the use of this new lines? I already told you that it might be possible there is more than one bounding box present in one images, but among those bounding boxes it may be possible that one bounding box area is equal to 0. So we have to remove that particular line, not entire annotation file. How we are doing? So I have just kept this store valid bounding boxes. Now just open the image. This way I am fetching the image path. And why I am using this means why I am opening the images, because I want to fetch this width and height to unnormalize that those bounding box values and easy to calculate the area. Now open the file in reading mode, and F basically contain all the details. This all details is kept in F. Now I have to iterate to this F so that I will get line by line. First line will contain this value. The second iteration will take this value. Second iteration, third iteration this line. Okay, this way we fetch the details line by line. Now data.line.spread. If suppose I just print line here, print line print line, just give me this thing in a string format, not in a list format. So let me show you. See this line is in a string format. Now here see data is in a list format which contain a string. Okay, so this values 1 value 0.675, this value will come into a list format, and and index at each index value this value is present. We can easily fetch these values. Okay, data is or 0, we can say this is data containing the string. So we have to convert this in an int format. So that's why I am using here int class index. Just give me that class index value in an int format. First value I will do, this is a class index. Now just see x center, y center, box width and box height. Basically what is happening here, just two value is the x center and y center. The last two values is the width and height of the image. Now we have multiply with width and height just to unnormalize them. Okay, this way details of the bounding box is fetched. Now this is x min and y min. What is the use of this x min and y min? Okay, x max and y min basically का top left corner, and x max and y max is basically the top right, not bottom right corner coordinates. Okay, now how we can fetch this, how we can calculate these values? See this x min. Now what is the mean of x min? X min is the top it is a top left corner coordinates, x coordinate. So how we have to reach up for up, we have to minus the box width by divide by 2 to move towards the left side of the towards the left side of the bounding box. We have to minus the box width divided by 2. Now x y min, I already told you in all my videos, in videos where I explain you how you can calculate the bounding box coordinates. In all videos I told you that for the by coordinates in images is 0 0 coordinate start from the top left corner. 0 0 index start from the top left corner of the image. So how to get the bi-mean? Just minus the box height with the divide by 2. This way you get the bi-mean. And for x-min, just move to the right side, we have to add. Y-max, just move down to the images, we have to add box height with the height by 2. This way we get the coordinates. Okay, now to how to calculate the area, just a x-min, y-min, and y-max in minus y-min. Okay, this way you calculate the area. Now you now you will say that why there is a need of this whole calculation. Just directly multiply width and height, you will get the bounding box. You will say that. Okay, so but I kept this just to explain, just for the explanation. So don't worry, you will directly able to calculate the area. Just multiply width and height, you will directly get the area of the bounding box. Okay, but there is one problem. For getting this x min and y max, x max, you have to calculate this thing also, because using this width and height and multiplying, you just get the area of the image. But for getting the area of the bounding box, you have to calculate these values. It's necessary. So after calculating the area, you just get the convert it into format, because this values will be in a float, so we have to convert it into value. If area is greater than 0, it means that particular line bounding box values are correct. Now that's where we have to append those bounding box values in the new list, new lines. Okay, just append them, and this dot join map string data convert back to the string format, and after every index value it will throw this space. Okay, this way particular line is we get the particular line. Now after say this, after opening the annotation file, after reading all the lines by 4x4, getting a new line list where each index is a correct, you can say correct bounding box whose area is less than whose area is greater than 0. We have get those. Okay, now see, after getting this, after iteration of with whole annotation file, if a new file, if suppose new lines is there, means correct annotation details is present, we open that annotation file in write mode and append and write that new lines with the proper formatting. Means see this new line, we have to first give the new line, then after that we have to give the new line. This way we write the detail line by line, not just directly paste all things without a line by line. Okay, so we have to make sure that line after when we write in a annotation file, line is there. Now suppose this whole thing is there, what is it, why I'm just removing the annotation file? Suppose all the annotation details, bounding box details area is equal to 0 or less than 0, we do not need that annotation file. So just remove that annotation file if suppose no valid annotation remain. Okay, this way pre-processing on the annotation file performed. Now just run this, we will get our details. See this, 838, 838. It means everything is fine. There is no annotation file is present whose image is not present. Second thing, and there is no annotation details present whose area is less than 0, or you can say less than or equal to 0. This way, our pre-processing on the annotation file is done. Now, this is a custom data set, which is a class which is used by the data loader to load the data. Okay. See, this is an image directory. This is annotations which contain all the annotation file name. This is annotation directory. Transform, basically if any process is required on an image, we have to perform that. This whole thing is the initializations. Now this length basically give me the length of how many images is present, or we can say how many annotation file present in a train directory. Now get this cat item. You can say this is an important function in our class which is able to return the images with the targets, which targets contain is a dictionary which contain bounding boxes and labels details. See, IDX basically you can see the index value of the annotation file. Now first we have to get the annotation file name. Just convert that annotation file name in an image path. Just annotation directory. Just last we do not want last four character, so -4, and add that -4 with the JPG. This way the catenation take place and we fetch the image path. Now open the image path if suppose image is there, otherwise it will throw the error. Now see this, when we open this image in a CB2 means OpenCV, it will read the image in a BGR format, so we have to convert that in a RGB format using this CBT color format, CBT function, CBT color function. Now this image shape, height and width. Now this annotation file, to open the annotation file to fetch the details we have to open it. Okay, this boxes and labels I already told you, this empty list where we'll append bounding box details and the labels. I already explained this whole thing above in the code. Till here I explain you. After getting the boxes details, just append those xmin and ymix, and xmin and ymix I already told you these are the top left corner and bottom right corners. And see what I am doing here, label.append class. I am not directly appending the class index what is present in the annotation detail, but I am adding 1+1 here because 0 index is already fixed for the background. So other and the other classes which we have is RGB, WC and platelets, so we have to make sure that 0 index is already fixed for background. So as for RCB +1, for BWC, all those indexes present in that annotation flight, just add +1. Okay, after getting this, just make sure you have to convert them in a tensor format for because we are using PyTorch, and PyTorch in all PyTorch all computation perform in a tensor format. Self.transform, I already told you, if suppose any transformation is there on an image, we have to apply that. After getting this, just make the dictionary, target dictionary. We have two keys there, boxes and labels, and return images and target. This way your custom class is ready for you by which is used by the data loader. Now this is the important part. This is a, you can say, model which we will which I will explain you. So let me open this in a VS Code, because here scrolling on a model and zooming it's might be a problem for me. So let me open this in a VS Code and explain you properly what is the use of this in channel num anchors, why we are fetching this. I will explain you all things line by line, so don't worry. So friends, so let me the model which we are using for the detection is SSD 300, which is 16, has a backbone, and the weights which we are using is Coco V1. I already told you. See this, 0 index value is for the background. I already explained you. Now first thing is in channel. We have to, for in channel, we have to retrieve out channel of all the sequential layer, last layer. Mind my words, I will explain you again. We want out channels of all the sequential layers, last layer. Okay, now just pass the model backbone and size which we want 300. Now number of anchors is basically give me that how many number of anchors is for the location, number of anchors present at a particular location. Number of anchors is that suppose there is a center as a location, so how many bounding box has an anchor has to be there for the detection of the object. Okay, so after fetching this, just pass this in channel num channel in this. Now let me explain you more detail in a more detail. Okay, say this. See, first see the model. This is the model of the BGT16 with the SSD. It has, you can see this is the SSD backbone, and these are the sequential layers. Okay, conversion layers. This 256, and this all layers. See this all layers. This first sequential, second sequential, third sequential is connected to the detection part. See, all layers is connected to the detection part. Now let me show you, and this whole part is a head. Let me show you this thing now. See this. So this thing from here till here, this is the head. Okay, now this thing, this layers is, you can say, the connections. Now see, now you will get confused as here input is output of this first layer is 364, but here inside input it is input is 1024. How does this happen? Because in convolutional, when we connect them, input channel of not output of the first channel is the input of the second okay, second layer. So how this happens? See this. I already told you that all layers, sequential layers, is connected to a connection head. So see this. Let me show you. See this. This is the first sequential. Start from here and add it. Oh, sorry. And it here. See this. Output of this last layer is 512. So this 512 of output is act as the input of this first layer. Now see this. Now second sequential, here's last layer is this one, and here output is 102 for this, and this output is act as the in channel for the second layer. Same way, the sequential last layer output is 512. Output is 512, so it act as an input for this layer. Now same way here, 256, and 256. 256, 256, 256. Now engine is calculated. So how many layers is connected to that head, and what is the input channel of that. See, now how we have to calculate the out channel. Let me show you this thing also. For that purpose only, we have to retrieve the num anchors, which tell us how many anchors is present at particular location. So let me show you this thing also. See this in channel. First we have fetch 512, 1024, 512, 256, 256. See this. After using this print statement in here, see this print statement in channel num anchors. I fetch the details. Now this am anchors. First layer basically is having four anchors per location. Means 4 bounding boxes has to be there at per location. Say now let me show you 4 anchors, 364. Now when we multiply and each conventional layer is act as a classification. So how many classes we have in Coco dataset? We have 91 classes. When you multiply 91 into 4 here, 4 is, you can say, anchor per location. 364 for the first one. Now let me show you the second. For the second we have 6. When you and 6 and how many classes we have? 91. See, 5, 4, 6 and 364, 364, because last two layer have 4, 4. Now this is you can say this is a classification hand where I explained you. Now this is a regression hand. 512, I already told you 512, 1024, 256, 256, how it's come. Now how to calculate 16 out channel? See this 16. Bounding box have 4 coordinates, x1, y1, y1, x2, y2, and x1, y, and number of anchors we have. Same here, same thing. 4 into 4 for first layer, 4 into 4, 16. For the second layer, 6 into 4, 24, 24, 24, 6, 24. This way the regression hand and classification needs the in channel and number of anchors, and I already explained you why we are calculating them. So I hope I explained you more detail what's the use of this integer and number of anchors after calculation time. Just pass this. This way it's you can say this make the SSD classification head according to our number of classes which we have. Okay, so this is a transformation of bin size of and maximum size which we passing it, return the model, it will return the model and just print the model. And number of classes we have 4. Why? Because background, RBC, WBC, platelets, 4 classes. And the size we want is 640. So let me run it. It display the model after pre-processing after changes according to our number of classes which we have. Say this now the classification had and you can see the regression had classification had see 16 24 24 24. Why? Because we have 4 classes and first layer contain 4 anchor boxes, so 4 into 4 16. Same way see this, let me show you. See this number of anchor boxes. So 4 6 6 6 6 4 4. So last 4 number of classes we have 4 and last layer see this third layer last layer contains 6. Third layer contains 6 anchor boxes, so 6 into 4 24. Now regression head, same way regression head 4 anchor boxes and multiply by 4. By we are multiplying here 4. Here we are multiplying according to a number of classes here. Here we are multiplying according to a coordinates of the bounding box x1 y1 x2 y2. That's why we are multiplying here 4 with each value of anchor boxes. So let me know that you explain it more clearly. So let me now move to this part. Here we are creating a data loader. So let's get started. See, this is a train image directory, there are annotation directory, list all the train annotation directory. Okay. Now we are creating here train dataset. You can say the object of custom dataset. Just pass the train image directory, train annotation directory, transformer. Just convert that image into a two tensor. Means converting time into an image into a tensor format. Okay. Now here just we are using a data loader not package library and just pass the object. Batch size will be 4 and suffering will be there. Batch size is 4. You can say each batch contain 4 images. Let me run it. Now just get the length 210. Here 210 means 210 is batches and each batch contain 4 images. Now this we are using the optimizer. You can say LR optimizer. Okay, this is a device this is a line which give me the detail that which device we are using. Either we are using GPU or either we are using a CPU. And same way after getting the device, just to make sure that model is on the same device. And this param means each parameter have one attribute required grade, which tell that particular parameter is updatable during training or not. If suppose required grade value is false, see required grade is a bool data type. It means true false is there only. So if suppose required grade value is false, it means that particular parameter or the weights do not has to be updated during training. So we this line basically make the list of all the parameters which is trainable during training time. Just pass this params in optimizer. The optimizer which we use is SGD. Build learning rate is 001 and momentum is 0.9. And here we are using a scheduler, torch.optim LR scheduler, step R. Okay, now just pass the optimizer, which is because optimizer, why we are passing here optimizer, because optimizer is responsible for changing the weights, and during changing the weights we require one thing is their learning rate value. So that's why. Now step size, what is the use of step size here? Step size basically give me the detail that after which interval, after which epoch learning rate value has to be updated. Yes, step size 3 means after third epoch learning rate value should be updated, and gamma here 0.1 means learning rate value multiplied with 0.1. Say this, epoch 1 001, epoch 2 001, epoch 3 after third epoch interval is complete, third epoch multiplied with 0.1, its new learning rate value is this. Same way this epoch is act as a first. Now this epoch has act as a second, this third. After third epoch just multiply by 0.1. This way the learning rate value changes. But here's one thing that I will uh, train it with 50 epoch. Let me run it. Now we have to test our data loader that mapping of the bounding box is correct, is had on a correct image or not. Okay, what is the use of patches? I will explain you. Don't worry. Here figure is representing the entire image. X is basically representing for ease of iteration over the subplots. 1 2, here we are just making 1 row 2 column, means only 2 images has to be represented. Now the figure size is 10 by 6. Now access.rev basically convert the dimension from 2D to 1D. Just I make the iterator of train data loader. Just pass the next. It will give me the detailed images, and target basically give me the detail of 4 images. This image contain 4 images. This target contain details of 4 images. Now see how many classes we have. BG, platelets, RBC, and WC. 0 index is for the BG, 1 index for the platelets, and 2 for RGB, and 3 for WBC. CMY, the color sample, means there is we can easily, you can say easily able to represent those classes. I give them the class color value differently. C for the platelets, M for the RBC, Y for the WC. Now you will get confused that how we can get the color for them. So don't worry, I will explain you. IDX range 2. See this. Using a transform, when we create a data loader, using a transform, it convert the image shape from HWC to CHW. But here I am so required HWC format. So to convert the CHW to our HWC, we are using permute here. Okay. And after getting this, we can get the targets, means dictionary of the labels in the bounding box using a IDX, then fetching the details using a keys. Just show the images, and suppose more than one bounding box has there, so more than one labels has, it is 100% more than one label be there, so we have to iterate over it, fetch the details, bounding box, x min, y min, x min, y max, then get the width and height of the image. Now see uses of patches here. We want patches of rectangle whose initial coordinates is x min, y min, and pass this width and height. It automatically make the bounding box. Okay, after getting the bounding box, just add it, and this text, just add a text of text. See here what's the use, text is class name and labels. Label basically I told it is give me the index value, so we will get the class name from here. And see for fetching this the color of this text will be K. Okay, now see this edge color sample, from color sample label label -1. What will be the what all be the label of the label of the image? It's will -1, because one label 1 means we want to define this, just -1. RBC for defining for defined M, we have to -1. So this way we fetch the color value. Now let me run it. See this WC, platelets. Okay, so this is some minute binder boxes, so but it's perfect. WBC, RBC. Okay, this way it's performing well. Now this is a main part which I will explain you in easy way. So don't just iterate over the number of epochs. The number of epochs which we are using here is 50. Just print the masses. Model.train make it say model train is make sure that model is in training mode, and there is an updation on the weights has to be performed during training. Now train learning losses, initially it is 0. Now print the masses. Now we have to iterate over train data loader. After iterating over train data loader, just these 2 lines give me the information that model images, targets, and sorry, this enough model training images has to be on a same device. That's why I use that particular line, device if CUDA available. That's line. This line tell us that which device we are using, CUDA or our CPU. So make sure all thing has to be on the same device. Just pass the model images in targets. It give me the dictionary of the losses, and after getting the dictionary of the losses, just sum up all the losses which is present on a loss detector, Okay, this optimizer zero grade basically convert the gradient value to zero. And why we have to use it? Because at each iteration over the batch, gradient value has to be zero before updation of the weights. Because if suppose the gradient value is not zero, it will accumulate it with the new gradient value of the new batch iteration and disturb the updation of the weights. Okay, so that's why. Now losses dot backward basically you can say calculate the weights value, not update the value, calculate the weights value. Now optimizer dot step basically update the weights value. Now just add the training learning loss with losses of item. It will, you can say this will add the losses of all the four images. Okay, after using this cellular, just give the cellular step at every third report. It will update the learning rate value. Now just append that. Now just print the train loss divided by the train data set. Now, why we are not multiplying with the length of the trained dataset loader? Because here we are not calculating the loss of each batch, but here we are calculating the loss of all images. So that's why we have to multiply with trained dataset. The trained dataset give me all length of all images present in that particular dataset. Now one thing that you will get confused, that what is how many losses is present in SSD. So let me show you that. Okay. And one more thing. So let me run it. Say this. SSD have only two loss: bounding box regression loss and a classification loss. Because we have only two head, means in head we have two thing only: classification head and regression head. So that's why it's having only two loss. After editing means 10.9 and plus 1.0, it will show me 11.9 only. So this thing happen. This way losses is calculated. This way losses is added from in losses and lost it. Let me comment it and run it. We do not need breaks here now because I already explained you. So let me run it. Now it's training gets started till 50 epoch. After that we will save the model, not faster RCNN. Okay, this will be SSD. Okay, same way here SSD. Okay, now let me explain you this thing. Now the same thing, first line, whether tell me that which device we are using, CUDA and CPU. Now you will get confused that why we do not directly use the weight and made a prediction, but that's not going to be happen because those only have a weights, but the architecture of the model is not there. So to first we have to make the architecture, and just then after that only we have to upload the model. So that's why first we have to make the architecture. For making the architecture of the model, we have to use the create function, create model, which I had explained you above in a code which we have made. So classes we have 4, we want 640. Just this will be the get the architecture of the model. Now load the weights which we have, which we will save. Now model.eval, because model.eval means model is an evaluation mode where the updation of the weights does not perform. Then this whole thing, this thing is important. This thing is that what all the performation done on the images has to be performed during training, otherwise during testing, not training, testing, otherwise it will throw an error. So what we only perform one thing, transformation, is that converting image into tensor. Testing is happening here. This is a test directory, but images is not there. I think yes, images will be there, because in test images and label both folder there, but we need the images. And this whole thing I have explained you: random choice of test directory, open the image, transformation, and see what is the use of unsqueeze. Unsqueeze is just a edge the wedge dimension, because when we pass the images during training, images variable is in a format of 430 640 into 640 into channel with channel. See, during training, this what I'm showing you here. During training, images variable will be shape is 4, and what is the dimension of that? Let me see this. Dimension is CHW. Dimension is 4, 3, 640, 640. Okay, after using a tensor, let's print it so that there's no need. Okay, so after using a tensor, its dimension of the image is 640 till 3, 640, 640, 640. But during training, we also have a batch dimension in the images variable, which show us that particular batch contains how many images. But here we are using only one image. So we have to add the batch here. That for adding this 1 into 3 into 640 into 640, we are using unsquares here. Now just with no grade tell us that there is no gradient node operation. Just pass the image and fetch the first image predictions, just print it. Okay, now permutate, I already told you that I am sure required HWC format. So to convert that, we are using permutate here. This is a, you can say, prediction. This is prediction containing these keys with values. So fetch the details of that, and see, I think so colors is multiple, but I don't want any multiple colors. See. So though there is no need of this. Okay, suppose multiple boxes, multiple boxes there, multiple labels there, multiple labels there, multiple score is there, because score representing here is the score of the bounding box. Now here I only want those bounding boxes whose score is greater than 0.18, because if suppose I will not use it and directly you can say represent the bounding boxes. So there is a, you can say, there is lot of bounding box creation take place on single image, or you can say single object, but we do not want that. We will only want those bounding boxes whose score is greater than 0.8. So this way whole calculation take place. I already explained you above in a code. See this random choice colors, I think so there is no need of this. This is extra part. So let me first complete this 50 epochs and come back. Okay, so wait for that. So friends, training is completed. Last you can see that loss is 0.429. So let me save this model. Now let me run this to see that how our model is working on unseen dataset, unseen images. So let me show you one thing before showing the images. See, this is the images. Before that, let me show you one thing. See, from here, so this is a prediction of the last image. You can see that it first is a key boxes which contain the bounding box details, and second thing is you can the score of each bounding box. You can see the value 0.9, 0.9, and somewhere 0.02, 0.02, 0.0. This way bound scores of the bounding box, but we are representing, or you can say using about creating the bounding box only whose score is greater than 0.8, and these are the labels of each bounding box. Okay, so these are, say, this is the predictions of unseen datasets of a model. It's working fine. Yes, it's working fine. Okay, so this is the model which is completed. Now you can download this model and use anywhere you can. Okay, so please like, share, subscribe, please, because this motivates me to make more videos like this, where I will explain you uh, more models in deeper way. Okay, please like, share and subscribe. Thanks to all.